And welcome back. As we continue our cosmic journey, we of course have looked at some of the more modern telescopes, but today let's go dive in looking at some visible light detectors and instruments. So, when we want to start recording the cosmos to try to get some of that information and data, you have to understand when a telescope collects radiation from an astronomical source, it has to first detect it and then it has to measure it in some form. The first detector used for astronomical observations, of course, was the human eye. But the human eye is not perfect. It suffers from being connected to an imperfect device, our brain. Photography and modern electronic detectors have eliminated the quirks of human memory by making a permanent record of the information from the cosmos. The human memory can, forget things, we can misremember things, but we have something like photography and all these electronic things, it can be much more accurate, and it's not subject to interpretation by the brain. Now, the eye also suffers from taking in only a fraction of a second of information. So that fraction of a second lets light energy come into your eye before it sends that information off to your brain. Now, one important advantage of modern detectors is that the light from astronomical objects can be collected by that detector over a longer period of time in a technique called long exposure. In fact, we can do exposures of several hours, and these are actually required in order to detect the very faint objects in the cosmos because we need that long exposure to be able to gather that light because it's so faint. Now, we can use instrumentation to sort and spread the light that we receive. Before the light actually reaches the detector, astronomers normally use some kind of instrument to sort the light according to wavelength. And of course, we have different wavelengths, whether it's ultraviolet, visible, infrared, etc. The instrument may be simple as using color filters, which transmit light within a specified range of wavelengths. For example, let's say we have a red transparent plastic. This is a filter that we can put over that will only let the red light through and block all the other colors. Now, after the light passes through that filter, it's going to form an image that astronomers can then use to measure the apparent brightness and color of objects. Alternatively, the instrument between the telescope and detector may be one of several devices, such as a spectrometer, because it allows astronomers to measure the spectrum of a source of radiation. So whether though we're using a filter or we're using a spectrometer, both types are ultimately some kind of wavelength sorting instruments. They still need to have the detector, though, to record and measure the properties of the light. And so when we look at detectors, of course, we have either photographic or we have electronic detectors. Throughout most of the 20th century, photographic film or glass plates served as the prime astronomical detectors for photographing spectra or direct images of celestial objects. In a photographic plate, a light-sensitive chemical coating is applied to a piece of glass that, when you develop it, actually will provide a long-lasting record of that image. And at observatories around the world, there's vast collections of photographs that have preserved what the sky has looked like for the past 100 years. Now, photography represents a huge improvement over the human eye, but of course there's still limitations. Photographic films are inefficient. Only about 1% of the light that actually falls onto the film contributes to the chemical change that makes the image. The rest of the light is kind of wasted. Astronomers today, though, have much more efficient electronic detectors to record astronomical images. Most often, these changes are done through charge-coupled devices, or CCDs, which are like the detectors that are often used in your video camcorders or in digital cameras. CCDs actually provide much more accurate instruments of the brightness of astronomical objects, also in comparison to things like photography or the human eye. So with these charge-coupled devices, how they actually kind of work is that photons of radiation hit any part of the detector to generate a stream of charged particles that are then stored and counted at the end of the exposure. Each place where the radiation is counted is called a pixel, and modern detectors can count the photons in millions of pixels. So if we look at example A here, the CCD is a mere 300 micrometers thick, which is thinner than human hair, yet it holds more than 21 million pixels. And if we look at image B, this is a matrix of 42 CCDs, and these are what actually are aboard the Kepler telescope. Now, CCDs typically record as much of 60 to 70% of all the photons that strike them. So that's a much bigger capture rate than what we saw previously when we said it's like 1%. So we have a much better image here. And because we can capture so much more, we can detect fainter objects such as the many moons around other planets, icy dwarf planets beyond Pluto, and even dwarf galaxies of stars. Now, of course, visible light is only one piece of the equation. Infrared observations are a very important thing to note, because observing the universe in the infrared band of the spectrum presents some additional challenges. The infrared region extends from near 1 micrometer, which is about the long wavelength sensitivity of both CCDs and photography, to 100 micrometers or longer. The main challenge that astronomers have when using infrared is to distinguish between the tiny amount of heat radiation that reaches Earth from stars and galaxies and the much greater heat that is radiated by the telescope itself and our own planet's atmosphere. Now, typical temperatures on Earth's surface are near 300 Kelvin, and the atmosphere through which observations are made are only just a little cooler. Now, according to Wien's law, the telescope, the observatory, and even the sky are radiating infrared energy with a peak wavelength of about 10 micrometers. Now, to infrared eyes, everything on Earth is brightly aglow. It's got this faint aura to it. So the challenge that astronomers have is to detect faint cosmic sources against this giant sea of infrared light. So if we actually had infrared eyes, what would this look like? Well, infrared waves can penetrate places in the universe in which light is blocked, as shown in this image, where the plastic bag blocks visible light, but it doesn't block infrared. So to solve this problem, astronomers must protect the infrared detector from nearby radiation. Since anything warm radiates infrared energy, the detector must be isolated in very cold surroundings. Often the detector is held in near absolute zero by immersing it in liquid helium. The second step is to reduce the radiation emitted by the telescope structure itself and the optics, and to block this heat from reaching the infrared detector. And of course, this is where our friend spectroscopy can start coming in. So this provides information about the composition, temperature, motion, and other characteristics of celestial objects. Light from the source enters the instrument through a small hole or narrow slit and is made into a beam of parallel rays by a lens. The light then passes through a prism, producing our spectrum. Now, a second lens can be placed behind the prism to focus the many different images of the slit or enters the hole into a CCD or other detecting device. Now, this collection of images is the spectrum that astronomers can then analyze.